Okay, so this is a video on A2 chemistry equilibrium, looking at Kc, so the equilibrium constants of homogeneous systems. So homogeneous systems are systems where the reactants and the products are in the same physical state. You don't have to study heterogeneous heterogeneous equilibrium at A2 level. So this is kind of moving on from your appreciation of equilibrium at GCSE and then AS level, which is very much around qualitative approach, so descriptive approach, and we use Le Chatelier's principle to describe if you made a change to a particular condition within an equilibrium, how would and why would that equilibrium move or respond. And then you also had to write some Kc expressions and work out units at AS level, moving on from GCSE. So at A2 level it becomes very much more quantitative, so we're going to be dealing with numbers. So instead of saying an equilibrium moves to the left or moves to the right, we're actually going to be able to generate numbers or values to give you a measure to what extent that equilibrium actually moves to the left or to the right. So we'll look at a variety of things here, and we'll go through the very bit of qualitative approach to equilibrium and writing Kcs and working out units of Kcs. And then to actually working out the value of the Kc itself, the actually numerical value. And then at the end of this PowerPoint we'll have a look at some past paper questions. I've got a mix of past paper questions in there, from very straightforward, fairly simple ones to some of the more challenging ones that you would meet at A level. So the equilibrium law is essentially relates mathematical quantities or mathematical concentrations, molar concentration of reactants to products at the equilibrium. Okay, so you've done this before in terms of Kc expressions. When we talk about equilibrium concentrations, we talk about using concentrations in the Kc expression. The convention is that we put that into the x, whatever x happens to be, into square brackets. And square brackets is an accepted convention within this equilibrium law, that it means the concentration of whatever x is. Okay, so for example, if we had a simple equation of m moles of A reacting with n moles of B to give us p moles of C and q moles of D, that would give us what we call an equilibrium expression or a Kc expression as so. So we're looking at the relative molar quantities of products compared to our reactants, essentially. Okay, and that is a constant at a particular temperature. Okay, and it is independent of, as you say, there's independent of initial concentration. So it doesn't matter what concentrations of A and B I start off with. At a particular temperature, this equilibrium will always set up and will always produce this constant. The constant is called the Kc constant, and clearly, hopefully, as you can see there, the bigger that this number is, the more of C and D there is. The smaller the Kc expression, the more A and B there will be. So basically, the larger the Kc, the further the equilibrium lies to the product side or to the right hand side. The smaller the Kc, obviously, the further it lies to the left hand side. So values of Kc for a particular reaction only if the temperature changes is when that Kc expression changes. So the concentrations changing the concentrations do not change the Kc, only changing the temperature. And that's important for lots of questions that come up. The other, if I change concentration, etc., pressure, etc., the equilibrium will shift, but it will form a new equilibrium, but that new equilibrium will have the same Kc value. It will have the same relative amounts of reactants to products. Okay, so what we're going to do here is we're just going to write a few Kc expressions. Okay, so it might be an idea, if you're confident with these from your AS chemistry, it might be an idea just to pause the video here now and do them. What I'll do is I will just go through them. So maybe if you wanted to see how to do one from last year, you might have a look at that, perhaps the first one here, and then pause the video and then do them. So I'll just go through them here. If you want to pause the video at any point, do so, and then you can come back and check your answers. So the Kc for this one, very simple. Okay, SO2 in square brackets to the power of 2, obviously 2 comes from here, oxygen, the 1 comes from there, and then our SO3 on the bottom line to there. Okay, our units, on the top line we have moles to the dm cube. Remember, that's the units of concentration, so we have moles to the dm cubed squared here on the bottom, and we have moles to the dm cubed to the power of 1 there, okay, and on the bottom line we have moles to the dm cubed squared. So you'll cancel the moles to the dm cubed squared on the top line and on the bottom line, and then you will end up with moles to dm to the minus 3 over 1 on the top line, which is of course as so. Okay, so I'll do the second and third ones here. I'll just go through them. I'll not talk you through these because they hopefully are fairly straightforward. Okay, so that's our Kc expression. Okay, and we would cancel and cancel, and we'll end up with 1 over moles to the dm to the minus 3 squared. Okay, and that becomes moles to the 2 dm to the 1 over, moles to the 2 dm to the minus 6, and that becomes moles to the minus 2 dm to the 6. Okay, so just for those of you who are mathematically not so confident, a 2 outside, if we're squaring that, then we multiply it. Okay, so that becomes to the 2, and that becomes to the minus 6, and then because it's 1 over, it becomes moles from the 2 to minus 2, get rid of that, and then moles from the minus 6 comes to the 6. Okay, and then our final one, very simple. Again, we will cancel the units there, and we will cancel the units there, and that will leave us moles to the dm to the minus 3 on the top line divided by 1, okay, which just leaves us moles dm to the minus 3. Okay, right, what about if we reversed an equation, and if they asked us for the Kc for the reverse of the reaction? Well, I mean, that's dead easy. All you do is you invert the Kc that you had originally. You invert the units. So for example, okay, moles would be the reverse of that would be very simple, and you would inverse the units. If they asked you, if you did actually work out the value for the Kc, let's say for example up here it was 10, well then rather than crunch all the numbers again for the Kc down here for the reverse reaction, it simply becomes 1 over 10. Okay, so dead easy. And then they do often ask you that, what is the Kc for the reverse reaction? And some people will waste their time taking the number from here, 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 and putting them in and putting that into their calculator again, when really all they have to do is 1 over the original Kc. Okay, so we'll have a look at this. So if we have a look at this slide and these few exercises in this slide, guys, first thing that we look at, or that I would suggest that you look at whenever you get a question like this, which is basically giving you the reaction of sulfur trioxide, or the decomposition of sulfur trioxide to sulfur dioxide and oxygen. First thing you look, everything is gas, so everything's homogeneous in the gases, so this is going to be susceptible to changes in pressure. Okay, next thing you look at is the number of moles on the left, which is 2, number of moles on the right, which is 3. Okay, then hopefully you remember that if you increase the pressure, the equilibrium will shift to the side of least moles. Okay, so if you increase the pressure here, the equilibrium will shift to the left, so 3 to 2. Alright, so, or least gas moles, I suppose I should say. Okay, right, the second thing that you're looking for here is we have a delta H which is positive, and you should all know that positive delta H's are endothermic. And then you should recall your knowledge from last year that endothermic reactions or equilibriums will move towards the endothermic reaction. If we increase the temperature, the equilibrium will move towards the endothermic side. So essentially this equilibrium that we're looking at here, we would, to encourage that to move to the right hand side to give us as high yield as possible, we would run that at a LP, a low pressure, and we would run it at a high temperature. Okay, right, well let's look at what happens here. So you might want to pause the video again and do some predictions here as to what happens to the position of the equilibrium. You can see the questions asking us, does the position of equilibrium move towards or away from products? And does the Kc increase, decrease, or is it simply unaffected? So let's say we're going to add, let me just clear this screen. So the first thing we're going to do is we're going to add more oxygen. So you want to pause the video and I'll go through these, and that will move to the side of the reactants. Add more oxygen, equilibrium tries to remove it. Okay, in that instance the Kc does not change. Remember we said earlier, Kc changes only with a change in temperature. Okay, that makes life easier. Adding SO3, we add some SO3, we remove SO3, the equilibrium tries to make SO3. How does it do it? Equilibrium moves to the left. Kc doesn't change. We add some, we take away our SO2, so we take away our SO2, the equilibrium will try and replace it. How does it do that? It moves to the side of the products. Again, Kc doesn't change. Pressure this time is increased. We said earlier that if you increase the pressure, it moves to the side of the least gas moles. So therefore it will move to the left hand side to the reactants, and again Kc doesn't change. Temperature increased, we said earlier if you increase temperature it moves to the endothermic side. That is this side, the right hand side. Forward reaction, so you get more products. Kc this time will change. We have more products on the top line of our Kc expression. Okay, we've increased those, we have less reactants. Okay, so therefore this time our Kc will indeed increase. Okay, and our final one is that we add a catalyst. Well, if you remember from last year, a catalyst will indeed speed up the forward reaction and the reverse reaction to equal amounts. The equilibrium will not change, the Kc will not change. Okay, so there's another one very similar. You maybe want to pause the video now, having had done the last one, and have a go at this one. Okay, so there's the answers. You can check those. Make sure that you're along the right lines. Okay, should have been pretty straightforward for any A2 chemistry student. Okay, right, now let's start putting this all into a bit of an application here. So, first thing, we have two reactions, okay? Reaction 1, reaction 2, and we have some information about reaction 1 and reaction 2 and the Kc value at temperatures as we go down and we increase the temperatures. Okay, so maybe if you pause the video, guys, it would be a good idea and do these questions, and then I will bring up the answers. So if you want to pause the video there now. Okay, so Kc expression for reaction 1 is that, Kc expression for reaction 2 is that. Very simple, we've done some of those already. You want to work out the units then. Okay, so moles to the 1 dm to the minus 3, moles to the minus 2 dm to the 6. Is reaction 1 exo or endothermic? Well, it's an endothermic reaction because, as you can see, as I increase the temperature, the Kc increases massively. Okay, so as I increase the temperature, the Kc is increasing, so the equilibrium is going to the right hand side as I increase the temperature, so therefore it goes towards the endothermic side. So reaction 1 must indeed be an endothermic reaction. If we look at reaction 2, as I increase the temperature, the Kc is decreasing, okay, quite significantly. So the Kc is decreasing, which means that the equilibrium must, as you increase the temperature, it must be moving to the left hand side. Okay, so the left hand side therefore must be the endothermic direction, so the forward reaction is of course exothermic. Okay, right, so there's a few questions there. I'll just leave them up. I think you want to pause the video, okay, and then I'll bring up the answers to them. These should be again fairly straightforward for any A2 student having gone through this video. Okay, so pretty straightforward, I hope, anyway, yeah. Okay, again, there's some more questions, checkpoint questions, if you want to pause the video and have a go at those. So pause the video now. Okay, so hopefully those caused you no problems, all fairly straightforward I think. Okay, so this is a good question here. It does cause students a little bit of problem because there's a wee bit more going on here. I'll just tidy this graph a little bit. So the percentage yield is the y-axis, the temperature, okay, is indeed the x-axis. So the first question is, we had to deduce whether the forward reaction involves an increase or a decrease in the number of moles. Okay, so if we'll just say it's, I don't know, A plus B going to C plus D. And if we look at it, the percentage yield as we so if we just take a constant temperature, so we'll just go down here and take a constant temperature. So as we increase the pressure, okay, our yield becomes less. So we go from 20 megapascals to 40 megapascals to 60 megapascals at a constant temperature. So what we're saying here, as we increase the pressure, we decrease the yield. Okay, so that means as we increase the pressure, it moves to the side with fewer moles. So therefore, if the yield is decreasing, we must have fewer moles on the left hand side. Okay, so the question here is whether the forward reaction involves an increase or a decrease in the number of moles. Well, the forward reaction must be more moles on the right hand side. Okay, so therefore that means that it must be a forward reaction where the number of moles increases. Okay, right, so that's exactly what we said. Right, next question then, I'll just leave that answer up, I'll clear my writing off it. Okay, so the next thing is use the diagram to deduce whether forward reaction is exo or endothermic. So this time we're looking at temperature. So we look at the constant pressure, so we'll just take one pressure line. Okay, and as I increase the temperature, okay, so if I increase the temperature, okay, I also increase the yield. Okay, and that, as we said earlier, is reflective of an endothermic reaction. So the forward reaction in this instance is endothermic. Our explanation is very simply that as we increase the temperature, we increase the yield, and that is reflective of or typical of an endothermic reaction. Okay, right, so again, another fairly simple question there. I'll leave that up, you can have a go at it. Okay, so you can pause the video there and check your answers to that. So pause the video now. Okay, so that's all the sort of introductory qualitative approach to the KC expressions and for homogeneous equilibrium systems. We're now going to move into actually crunching the numbers and doing some calculations, and then we're going to move into some past paper questions, some relatively straightforward ones, followed by some of the more challenging ones. Okay, so I've decided to put this on a second video, so there'll be a part 2 to the video, so if you want to log on or search that one up and have a look at that to deal with the calculations and the quantitative aspects of homogeneous KC.